Hello, friends. Uh, this is a video on how to connect kinetic energy, potential energy together, and how they connect to the wave function, and in reverse. And that's really important to understand that that's what we're doing. Um, oops, got it. So, um, so the first is if I draw a wave function, right? Then it comes from and connects to the kinetic energy, which comes from and connects to the potential energy. So you can do this one direction or the other. This is like the big concept. Um, Now we're going to utilize important things such as kinetic energy is this. It's the curvature of psi times these constants. Careful, there's a negative sign in front, divided by psi itself. Don't forget that it's divided by psi itself, but conceptually you can think of it as the curvature. That's in a previous video, and we're going to apply that today. Also, kinetic energy plus potential energy, of course, and this is easy, right, equals total energy. Make that really easy, and that this is constant, such that when kinetic energy goes up, potential energy goes down, and when kinetic energy goes down, potential energy goes up. They're opposites. And that's really important too. The third thing we're going to do is that force is the negative slope of potential energy. So if potential energy goes up very steeply or goes down very steeply, that corresponds to a large force. If it's very shallow or flat, that corresponds to a low, or if it's flat, a zero force. So all of those are uh, uh, everything that we're doing. So let's do some puzzles. So if I have constant velocity, a constant wavelength, right? We call that a free particle. That's just constant KE. And if potential energy is constant, that means kinetic energy is constant. That means potential energy is constant. And we might as well set it equal to zero. You don't have to, but it makes sense to set conventionally to set your minimum potential energy to zero. You probably did that in physics 1, where your lowest potential energy point you just set to zero to make your life easier, but you don't have to. It's just some constant value if the kinetic energy is constant. So here we have constant curvature. A constant wavelength means constant kinetic energy, and that means we have the same kinetic energy everywhere. So if we were to graph kinetic energy as a function, so this is a graph of psi of x as a function of x, separate graph. If I were to graph kinetic energy, it would just be some constant but positive value. So here kinetic energy is positive because when the curvature is negative, notice that psi is positive, but when the curvature is positive, psi is negative, right? That's important. Remember, I had a little video on that as well, and we did that in class. So that's important. So we have a positive constant kinetic energy. Great. Pause the video and rewind it if you need to, but that's that puzzle. What if I drew this? Let's say I have psi of x as a function of x. Sorry, that's a little messy, but you get it. That's psi. And let's say it starts out like this. And it goes like that, and it goes like that. Well, where the curvature is higher, this is large or maximum kinetic energy, more curvature. And here's less curvature, so here we have minimum kinetic energy. And then we have maximum kinetic energy here too. So now you want to think of forces. So pause and think, okay, slower here, faster here. That means the force is pointing out here. That means the force is pointing out here. If this were a real life a classical situation, and the real life version of this, I would just have some object that's experiencing forces pointing outward from some middle point. So how do we graph this? Well, first of all, kinetic energy and potential energy, we can put on the same graph, and we get that kinetic energy is minimum in the middle, not exactly zero, and it goes up on both sides. And potential energy does the opposite. Remember, they're just opposites of each other. So the minimum potential energy we'll say is zero on both sides like this. So this is a hill. This is a potential energy hill. So it's like balancing something on the top of a hill. The force is going to push it right, or the force is going to push it left. Notice the steepness increases here. The slope of potential energy is the force. And you can confirm the negative slope. If this is a negative slope here, negative times negative gives us a positive force over here. Near positive slope, right, times negative gives us a negative value here. So whatever the slope is, multiply by -1, you get the force, the instantaneous slope at any point. And here, there is no force in the middle because it's in equilibrium in the middle, but this is an unstable equilibrium. Right? So you can't, it's hard to balance. Great, that's that one. Pause that, rewind it until it makes sense. That was kind of a big deal, just going through that logic. Let's do this one. Let's say I have psi of x do something a little different, where it starts out big and it goes really skinny and then it goes big again. Well, same logic. I'm going to have low or minimum kinetic energy here, maximum kinetic energy here, and minimum kinetic energy here again. And if it goes to a constant wavelength, it goes to constant kinetic energy. If it just goes to flat, really wide, that means it went to zero kinetic energy and essentially stopped. But the point is we are speeding up now here. So here I have a force to the left, here I have a force to the right. Right, because I have maximum speed in the middle. So if I were to graph kinetic energy or potential energy on the same graph, which I think is informative, the kinetic energy would be maximum in the middle and would go towards zero on both sides. Whether it reaches zero is dependent on the situation, but the shape would look like that. And we have, therefore, minimum potential energy, because these are always opposite, and maximum potential energy here, max potential energy here. And the force always points from max PE to min PE. And so we have the potential energy where it's minimum, I'm going to set it equal to zero. Number minimum potential energy, I want equal to zero. This is just convention for ease. You don't have to, but it's easier to do. Whatever the kinetic energy does, the potential energy does the opposite. So that's PE. This is KE. And this is a bowl, right? This is stable. Because wherever it's going to go, say the object goes to the right, it's pushed back left. If it goes to the left, it pushes back right. So it just oscillates back and forth. This is also called an oscillator. So whatever oscillator you can think of, this is the potential kinetic energy graph for that, where if it gets pushed one way, or if it goes one way, it gets pushed back to the middle. Here, it gets pushed back to the middle. These are called restoring forces. And all of this came from where? This. We knew the wave function. So therefore we knew the kinetic energy, so we knew the potential energy. That's how we got this. I just drew a wave function. I just drew a bunch of wiggles, right? And notice that all of these have positive values of kinetic energy also. That's really important because they're wavy waves. That if psi is positive, curvature is negative. For all of these, we have positive kinetic energy. So it kind of begs the question, what is negative kinetic energy? I'll cover that here right now. So what is this mean? Well, this is called classically forbidden. So because in classical mechanics, you can't have negative kinetic energy because 1/2 mv squared, right, is always positive. But quantum mechanically, it's allowed because if I keep increasing potential, I just decrease kinetic and mathematically it just goes negative. So what's a scenario like this? So say like in space, no gravity. I have a ball of mass m going at a speed v. This is the classical situation. And I have a wall of thickness d, and I have some force that the wall is exerting that's in the negative direction, which is going to slow the ball down, turn it around, and send it back the other way. It's just ball bouncing off wall. So if I were to graph potential energy, so now what we're doing is we're going the other way. Whereas here, I'm starting with the potential energy from the situation. So this comes from the forces, right? From forces. Okay? So the forces of existence create a potential energy, which determines kinetic energy, which determines the wave function. So here I'm doing it in reverse. So here, my potential energy graph looks like what? Well, I have 0, because this is a free particle, right? Constant potential energy, which I'll just set equal to, it's constant KE, constant PE, but I'll just set it equal to 0 for ease. Remember, that's for ease. So free particle, even though it's like a ball, whatever, it's a free object. So 0 potential energy here. And then we'll call this x equals d. The force is the slope of potential energy. Right? It's the negative slope of PE. So that means there's now some slope since there's some force. And since the kinetic energy is going to drop, the potential energy is going to go up. And technically, we'll just keep going up throughout the entire wall at a constant slope. Constant force means constant slope. Of PE. Great. So what does the graph of kinetic energy look like? Well, it does the opposite. So here we'll have x equals d. The other side of the wall, here we had some positive value of kinetic energy because it had some kinetic energy, right? It is positive, right? 1/2 mv squared. But then once it hits the wall, it starts to slow down and eventually stops, right? And then it would turn around and gain kinetic energy back in the other direction. But this kinetic energy graph is perfect to represent kinetic energy as a function of distance. And it would stop right around here. Whatever this value of kinetic energy is determines how far it goes up this potential energy hill, how far it goes into the wall, right? But what if it kept going? Well, that means the kinetic energy would continue to decrease at a constant slope. I'm just trying to extend it here. I think I'm going to erase that and redraw it. It's going to extend downward, right? Like that. And here it's going to be 0, but here it's negative. So what does that mean? And classically, it wouldn't ever get there. Classically, it would stop here at kinetic energy equals 0 here. That would be the same value once potential energy maximized, kinetic energy got to 0. So whatever initial kinetic energy it came in on determines how far it goes in. According to the wave equation, in terms of kinetic energy, if kinetic energy is less than 0, if psi is positive, remember there's a negative sign in the equation, then curvature is positive. So that's totally fine. And if psi is negative, then curvature is negative. That's totally fine. So what does that look like? Well, it looks like this. So if you have kinetic energy positive, these are the 4 options. I guess technically there's only 2 options, but really there's 4. Which is it's going to be what? Psi is positive, meaning it's up here, but curvature is positive. That's the smile, concave up. Or psi is negative, curvature is negative, concave down, right? So it's not going to be like full loops like this. It's always going to be one of these four sections. And really, maybe I should have drawn them as separate, but it's going to be exponential decay, e to the negative ax, or exponential growth, e to the ax, or negative, just flipped over the x-axis, negative exponential decay, or negative exponential growth. Those are the four options. It will always be one of those. And A determines that just a number in the exponent that determines how fast it decays or how fast it grows. So it's either going to be growth or decay. And then we have to ask ourselves, again, pause it, rewind. I'm just going to keep moving. We have to ask ourselves, what is smooth and physically real for the wave function? Meaning, so if I now have my kinetic energy like this, so now we're going to match kinetic energy to the wave function. What I did earlier in the video is I started with psi and I got Ke. Now I'm starting with Ke and I'm getting psi. And so what I want to do is do x equals d here, x equals d. And I'm going to graph kinetic energy as being some high value. And remember, it drops to 0 and then it continues negative, right? Here, therefore, free particle, what does that look like? A free particle, as we know, is a sine function, the constant wavelength. That's free. Great. We have constant kinetic energy, free particle. Great. It was free until it hit a wall. And once it hits the wall, it's going to slow down. When it slows down, what happens? It widens. So until kinetic energy equals 0, it's going to get wider, but only for a brief moment, right? Because it's like suddenly stopping, right? When a ball hits a wall, there's very little give. So it's going to widen a little bit, and then it's, so careful, psi being negative is not the same as kinetic energy being negative. Kinetic energy being negative brings us to these now. So which is it? Well, I have a positive value for psi here, which means I need a positive value for curvature. For kinetic energy is negative, this is what I need. For kinetic energy is positive, I get a wavy wave. For kinetic energy is negative, I get an exponential increase. So is it going to go up forever or is it going to decay? Well, if it goes up forever, it means it has infinite probability of going through the wall. That doesn't make any physically sense. That is not real. So the choice is, let's pick a good color for this. Ooh, I like the red. It's going to decay. So it's going to be e to the negative ax, something like that. Here will be some sine function, sine kx minus omega t, or probably a combo of, right? Like we have a free particle, wave, packet, or a combination of sine functions. Now we have a widened sine function, and here we have a decay, e to the negative ax. Which means, remember, what is psi? So psi, I'll actually just draw it here because I'm going to be done. Psi of x squared is the probability. So the amplitude of psi is the probability. So here we can interpret this as high probability, this is 0 probability, this is high probability, this is high probability that it hits the wall, but then exponentially decaying probability that it goes through. But it passes the kinetic energy equals 0 point. It passes this point, which is amazing. This is called tunneling. And all we did was apply this logic that we know. All we did was apply this logic. Please go back to the video and follow it. We get an exponential decay. And on the other side, we would get a lower amplitude, wider sine function. We can talk about that later. But here we have another free particle that's slower because the wall slowed it down and is slower probability because look, the probability amplitude is here, whereas it has to connect here. It's got to be smooth. It's got to connect. So here it connects here it connects here, and we have another free particle on the other side, just with lower probability, which means the electron can go through the wall. What? There's an exponentially decaying probability that it goes through the wall. So it's really tiny. It's very low, but you have enough electrons or enough time, or you do it as enough over and over again, it's going to go through, which means it's everywhere through the wall and on the other side. And if you measure it, there's a non-zero probability that it's going to be on the other side. Well, that's it. That's quantum tunneling. Close it. You touch something, you realize the boundary isn't well defined. Like the illusion of the solidity of all things is revealed in these wave equations, and I love it, right? Because it really wakes us up. When you zoom in, the structure of material becomes this false illusion of the classical mind. Anyway, I hope that made sense. Please rewind the video. But that was concise and everything there was important. Please have that and make sure it makes sense. See you guys on the other side. Later.